So once again, welcome Deb and Sarah. Thank you so much for coming today and making this happen. And everybody who's listening right now, welcome to you too. Deb and Sarah are both okay if you ask questions in between. I should be able to see your questions all the time and can transfer them if they don't see it. Otherwise, I would like to hand over to Sarah and Deb and have them introduce themselves and tell a little bit about their story. Please go ahead.
Okay,
oh,
so I'll...
Sorry, just one more second, Deb. Sorry. My name is Doris Schierberg. I don't know if everybody knows me already in the MITS program. I have taken over the Women in MITS webinars and hope to see a lot of you more in the future. We will do this about once a month from now on. Okay, now Deb, thank you.
No problem, and thanks for inviting us. So I'm Deb Agarwal. I work at Lawrence Berkeley National Laboratory. I have been there about 25, it might be 26 years now almost. I've worked in a lot of different capacities. I came in as so my background is computer science, and I've been a researcher at the lab for all of that time. I've since moved into management and have been a group lead and now a department head. So I lead our data science and technology department. That's both a research and applied department. I'm going to talk a little bit more focused on, my talk will be a little more toward the applied work that we do, but I think between Sarah and I will also mention some of the research aspects of it as well. And I think that my path. So my bachelor's was at Purdue, and it was in mechanical engineering. And I went out to work in industry for about 3.5 years at General Motors. And when I left General Motors, I went to graduate school at Purdue. And no, actually, my bachelor's was at Purdue. What am I saying? I went to graduate school at Santa Barbara. And what I always said about that is I went to Purdue to learn how to study, and I went to Santa Barbara to have something to do after I was done studying. But basically, then I did my master's and my PhD at Santa Barbara, and about halfway through, so I entered in mechanical engineering, and I left in computer engineering. Basically, what I realized is I didn't like mechanical engineering as a graduate student. I liked it as an undergrad. And I really enjoyed the computing side of things. And so partway through, I went and asked the assistant dean who had taught one of my classes if I could switch. And he said, sure. And so I switched. And I did my PhD in computer engineering, mostly a computer science topic. And I've really been working as a computer scientist ever since. You know, as might happen for many of you coming out of the information school, I think you're all information school graduates. Is that correct, Doris? Yeah, okay. You're muted, so you're not.
What I was saying, as far as I know, yes. I'm not sure what channels this has all been sent to, the invitation, but potentially School of Information only.
Okay. But what I've learned in my many years working as a computer scientist with very little of the background training in it is as long as you claim you are, you can be a computer scientist. So so for those of you who think maybe, well, I got an information science degree, maybe I'm not a computer scientist, don't let me tell you you're not. You can be what you want to be. That's one thing my career has certainly proved. So I'm going to turn that over to Sarah with that.
Thanks, Deb. That's quite an introduction to follow. So my name is Sarah Poon. I currently work also at the Lawrence Berkeley National Lab and in Deb's department. And I'm a bit of an unusual person just at the lab in general, and that my main focus area is in user experience design. But I guess I can call myself a computer scientist too. So my undergrad had nothing to do with any of this stuff. I went to UCLA and I was an econ major. I wasn't really that interested in it, but I just tried to push through and finish it off. And then I ended up working as a web developer in sort of the .com era, like small .coms. I was working for an online internet marketing company that was doing things like tracking pixels and those kinds of things. And, you know, as we know in history, the .com era, everybody eventually kind of crashed. And in any case, I kind of felt like I wanted to do something a little bit different, but I wasn't exactly sure what. And I ended up going back to school actually at the Berkeley High School. So I was a MIM student. There was no MIDS program back then. I graduated in 2006. And that's when I am assuming that a lot of people know a lot about the MIMS program, but it covers a lot of different topics. I particularly found the sort of HCI topics interesting. And I saw an advertisement for a student job at Berkeley Lab under Marty Hurst's a former student, Cecilia Aragon. And so that is when I first started working there. I was working directly with a physics group back then. After graduating, I think that I took a break and tried something else. And then I eventually got hired on in Deb's department, and I worked there for 8 years. I was initially doing more development than design. I was doing design and development at the same time. I was never a great engineer. I always was more interested in the design aspect and the user research. And eventually I got to the point where people were like, yes, this is important and this is necessary. So I got to do a lot more of that type of work. And then 8 years in, I decided that I wanted to explore some different areas. So I left and I went to work at Stitch Fix as a user experience designer in their expert use team. And I was primarily working with the merchandising team and with their internal warehouse operations. And that was a really good experience. I learned a lot. It was nice working with a lot of other designers. And then life happened and it didn't work out for me. And I eventually came back to Berkeley Lab, and that's where I am now today.
Thank you. We had agreed that Deb goes first, right?
Yeah.
Good.
So I'll go ahead and share. So I put together a short presentation to sort of give you some background about what we do, the lab a little bit, and sort of how we came to, Sarah's story was great because it sort of led into this talk very nicely. Okay, and you guys are probably seeing presenter mode, or you're not seeing the actual presentation? Yeah, so let me fix that first. No. Gosh darn it. This hasn't happened to me on Zoom. In fact, it didn't happen just a moment ago. Let me stop the share and try again. Sorry about that. That's not what I want. Okay, so now you should be seeing the presentation. Excellent. And you're going to see closed captioning on the bottom. That's something we've been turning on in case any of you have hearing issues that might help, or if your attention wanders because your kid just came and asked a question, you can always look back at the closed caption to see what the heck I'd been saying. All right, so I titled this talk, How I Learned That I Was Asking the Wrong Question, because about where I'm going to end is about where Sarah came in. because she really taught me that I was asking the wrong questions when I was engaging with scientists. And that's sort of the theme of what we do now. I mean, she actually had a major impact on how we approach working with the scientists. And I'm going to talk a lot about background of what we do and then how that came to be. All right, now the big question is, can I make the slides advance? Yes. So a little bit about the Berkeley Laboratory. It's actually the first of the national laboratories for Department of Energy, and it was started by Ernest Orlando Lawrence, which is part of why the name Lawrence. And why did he start it? He was down on campus. He was working with his research lab. You know, he was trying to understand matter. And he said, you know what, the type of machine I need is a cyclotron big enough that I can actually understand, you know, the next energies of particles and things like that. And I need to bring together a multidisciplinary team of engineers and physicists and all sorts of different domains to build this machine. So this is actually Lawrence's team in the original building that the first cyclotron was built in. And so the whole idea of the National Lab is to enable big team science. And that's really important in this whole story, which is why I wanted to sort of start you out with that idea. So just to give you an idea of what are some of the teams that I work with, just so you can get a feel for what do I mean by big team science. So one of the projects I work on is the Ameriflux Carbon Flux project. And the picture in the upper right, let's see, my cursor will work. All of these little dots are towers that are measuring carbon flux, and they're individual teams of scientists who have each chosen to put up a tower and measure this carbon flux. And they're actually all over the world. There's like 1,000 different towers around the world. And Ameriflux is just organizing all the ones in the Americas. And actually the person down here looking at his computer screen is actually Dennis Beldacki from down on campus here at Berkeley. And he has 7 of these towers that he runs. And the whole idea is to understand how this ecosystem that the tower is placed in, how it exchanges carbon with the atmosphere. And what are the dynamics that drive it, right? So this is about understanding things like climate change and understanding how more rain or more heat or longer summers or any of these types of things affect particular ecosystems. Like, so, you know, here this site is in a savanna area back toward the Central Valley. He's got sites in the Delta as well. So another big team project, this is a team that where most of the team is actually at Berkeley Lab, whereas the Ameriflux project, they're people from all over the world, different research teams. This is a research team where it's mostly people at Berkeley Lab, but about 40 people or so, 40 to 60, depending on the year. But what they're trying to do is they're looking at an upper Colorado watershed, so on the Colorado River, and trying to understand all the dynamics of what's going on in that watershed. So everything from the vegetation dynamics, the hydrology dynamics, the geochemistry, the microbes, and everything that, you know, and again, it's around sort of a climate change type topic where it's trying to understand in a drought, you know, how do the dynamics change? You know, how do the plants change? What do they do to, you know, to adjust to the drought? What happens in terms of the river flow, the chemistry, all those different pieces, the groundwater, and trying to understand, you know, how do the nutrients flow through the system in different situations. So another project that we have is, so within Department of Energy, there's a whole area called Environmental System Science, which the 2 projects I just mentioned are part of, but there's about 300 projects at any point in time across universities and across the national labs that are funded by this Environmental System Science program. And about 4 years ago, they came to the conclusion they really needed a data repository for their project. And so we proposed to be that repository, and we won the repository. So one of my projects is actually running that, you know, creating that repository and running that repository for all of these projects. So that gives you a feel for sort of a breadth of different projects. I mean, I've also worked on projects with astronomy, with high energy physics, with energy folks, you know, a broad array of different projects. We have about 16 different divisions up at the lab, and each of them work in a different area of science. So there's really a broad spectrum of different science activities, and we as computer scientists help enable a lot of that science and do base computer science research in what we do. So just showing some of the impact of what some of these teams do. Here's just some statistics looking at the Ameriflux data and what's going on. So this data collection started in around 1994 and has been being collected ever since. And you can see that there's a lot of data in this data set. And in fact, we have, you know, so we're actually, oh, that's number of Ameriflux sites. Yeah, we're up to we're up over 500 Ameriflux sites. And, you know, we have on the order of 4,700, actually it's much higher than that now. These are slightly older numbers, downloads of this data per month. You know, so it's used around the world by people to understand the dynamics of these ecosystems, to understand the data itself. And a lot of what we do in most of these projects is help with the computer science and the data management aspects of these projects. So we'll actually go in and be part of the team working on the project and providing some of that computing, modeling, or data management activities, or just data processing and things like that. So here's another project just to give you another view of something we're doing. One of the challenges that we have in California now is groundwater, right? I mean, you can't watch the news normally, non-COVID, and not hear something about water in California. I realize these days you can actually watch the news and not hear anything about water in California, but normally you can't. You know, and that's because you know, we've got all this agriculture going on in the Central Valley. We've got a desert in the Southern California, and we're trying to keep everything perfectly hydrated and beautiful, despite the fact it's a desert, despite, you know, all these other things. And so there's new regulation in California about managing that groundwater. And by the way, the pictures up the side are just some of the people working on some of these projects. I didn't try to do it on every project because sometimes there's just too many people to show. But I just to give you a feel for the sorts of teams I'm working on. But basically, the new regulation says that every county, actually it's a GSA is what they call them. Every region is supposed to manage their groundwater. And the whole idea is to cut down the overdrafting that's been going on, right? Where we've been continually decreasing the water level of, you know, in the ground, and it doesn't recover with the next rain. So every year our groundwater is going down, which is somewhat why when you go down Highway 5 and you look and you see the little sign that shows the different levels at different years, the ground is actually sinking because we've taken so much water out of the ground, right? And that's what all those levels are showing. And so with this new sigma is the regulation, all these different regions are supposed to be managing their groundwater to try to keep it not going down, you know, to keep it from going down and start to build back some of the groundwater. And that requires having a tool that allows you to make decisions about what's going on and what you're going to do. And so this was work to actually use machine learning to try and based on the data available about the groundwater, enable prediction of what's happening in the groundwater, so that then you could look at different scenarios or different mitigation techniques and be able to make predictions. And so this was a collaboration with some of our modeling teams to look at how can we use surrogate models, which are sort of fast running models that represent the data to enable us to help decision makers on this. So another thing we get involved in is looking at helping to quality assess data. Like this is from the watershed team. And this is this upper graph is water level data in a well. I mean, does anybody believe that that's an actual measurements of water level, right? I mean, no well is going to drop down that far instantaneously and then back up again, right? I mean, you'd have to have an amazing suction pump to drop the water level that much. And in fact, you know, it's things like that calibrations were, you know, were giving spurious data into the stream. You know, here there were things like that the calibrations had actually incorrectly calibrated the sensor and then recalibrated it to be correct. And so we often get things like this and then have to look at what can we do with this data stream? What's right and what isn't? What of it can we keep? Can we correct any of this? Right, so these are some of the questions we try to answer. Another thing we do in most of our projects is we end up building portals for enabling access to that data and trying to enable them to do science on that data, right? Make it much easier for them to do that science in terms of being able to find it, in terms of being able to plot it, and in terms of being able to analyze it. So those are usually our goals in these sort of projects. And the problem that occurs is when we, you know, so for, you know, I've now been engaging with scientists for 26 years trying to help them with problems. And the typical problem is they've been told and they've seen that computer science is magic, right? You know, we've produced all these amazing things and as far as they can tell, they just fell out of the sky and they're wonderful. And so, you know, when we go and talk to them, they imagine something amazing, right? Oh, well, we put 50 sensors out in the ground. Could you just hook them all up and give me graphs? You know, I mean, that's sort of the way they're thinking, because that doesn't seem very hard. Could you just do that? And so that's often what they're imagining, is that, you know, they can go out in the field and put all these instruments and then bring us in and they'll get this. They'll get this beautiful portal that just shows it to them ready for science. And early in my career, the way we engaged with computer scientists, or with the scientist, this is supposed to be the scientist over here, this is supposed to be the computer scientist, is we tended to be computer scientists funded to do a research project. And we thought that research project was pretty darn useful to science. And so we'd come in with an idea and we'd go talk to the scientist and they'd tell us about their science and we'd tell them about the cool thing we'd been doing. And we'd talk about how the cool thing we'd been doing could be useful to them. And we'd almost always come up with some way in which it'd be useful to them. And so then we would go off for lots and lots of time. You know, we'd usually, you know, spend about an hour with them, maybe a couple meetings, maybe we'd meet with them occasionally, but we'd largely have a pretty good idea what we needed. And we'd figure that we didn't really want to bother them until we could show them something concrete. And so we'd go off and we'd build some beautiful artifact and we'd write a paper about it and we'd present on it and all these wonderful things. And we'd show back up with the scientists. And the scientists would look at this beautiful thing and say, oh, that's awesome. That's really nice. And they'd even come and give talks about how nice this thing was for us. And at one point, we finally had a discussion in a strategy session where we talked about where we said, you know, I wonder how much impact we've actually had. I mean, we've done all these projects where these scientists love us. Let's go talk to them and find out how much we impacted. We found about 10% of our projects where, you know, scientists had just been raving about what we did. About 10% had survived and actually have been of use to the sciences. That was really an awakening moment for us when we did that and said, oh, huh. how could that be? Why would they have told us it was so great? And so it caused us to think a lot about what was happening in that relationship. And part of what was happening is that they're scientists. They love hearing about the cool things we're doing. They love thinking about new things they could be doing. And so that first interaction was fantastic for them because it expanded their mind. It taught them a bunch about computer science things. It allowed them to think about things they've never done before. And so they went off and dreamed. We went off and built concrete things. And we came back with their dream in some version of concrete. And 98% of the time we figured out we didn't know what the heck they needed because an hour conversation wasn't enough time. And also their problem had changed so much in the time it took us from when we left to when we showed back up that we were completely off base anyway. Even if their problem at that moment was what they told us, our going away and disappearing meant that they didn't know that we were still working on it, and therefore they didn't bother to tell us that in fact the problem had changed, or things like that. So I had this great opportunity to rethink what we were doing. We were doing the strategy session. It helped that this was a bad thing, but it helped. Our program manager actually retired. And this person had been funding our department at $5 million a year worth of projects. And when she retired, she was not replaced. So our department had the opportunity to think, what would we like to be doing now that we're not doing that? and we sat down and we said, you know what? We'd like to actually have more impact on the scientists than 10% of the things we build. And about the same time, Sarah and Cecilia both joined the department. And so we said, well, on a lot of these new projects, instead of being on our own money working for the science, we're gonna end up on their money. And we do really want to figure out how to make sure that we're doing something they need and they want to pay for. And so I'm going to cut the story short because I could tell you a whole long sorted piece of this, but basically we shifted completely to having that. In fact, we were looking at it from the HCI standpoint. And when I finally realized how valuable that was, I gave Sarah a project. And I said, Sarah, this particular engagement with the scientists, you're going to lead. And I'm going to sit in. Okay? And so we went to the first meeting with the scientists. And our view had always been, we don't want to waste their time. We want to spend as little time as possible bugging them and as much time as possible delivering something to them. And we sit down in this meeting. And about half an hour into the meeting, I'm absolutely positive we know everything there is to know about the problem. We know exactly what we'd start to build. And I'm about to tell Sarah, Sarah, we ought to go now. Because I think I can just tell you what we need to build and we'll be fine. But, I managed to hold my breath and wait. And Sarah asked this question. And I suddenly realized that she just flipped on its head everything I thought I knew. Because their answer was nothing that I thought was right. I said, okay, let's stick this out a little longer. But probably we now know what it is. And then Sarah asked another question. And I went, oh crap, I should just shut up. Because it was clear that I didn't even understand their problem. And that for me was really visceral, that I realized that not only did I not understand their problem, but I had never been understanding their problem to the extent I should have been. And so, then we watched Sarah go through this whole process of bringing back prototypes to the group and on paper, which we thought they'd kick us out of the room for bringing paper. Because it's like, are you kidding me? We're not even going to bring them something on the computer? No, we'll bring paper. They'll be fine. and I was incredulous because by about the third or fourth meeting, the scientists only cared about keeping the HCI people on the project. They actually wanted to kick all the computer scientists that we'd brought to the project off and just keep the HCI person because it was the only person who understood their problem. Everybody else seemed kind of useless. And the other thing we learned is that they were so dedicated to getting that thing that Sarah had finally, you know, reached through the paper prototypes, that they would pay whatever it took, for the most part, within reason. We computer scientists cost more than they do, so they don't like that part, but still. And it was just a visceral difference because we had people begging us to build what they had come up with instead of saying, yeah, I think that might be interesting. They were saying, oh, absolutely. I need that. And I need it now. Please build it. So I'm going to end there because that, I think, is about the best intro I can give Sarah. Because basically, like I said, she completely changed our approach in this by even just that experience made it so obvious to me that we had to completely change. And now we lead much more by the HCI approach because it just has made such a massive difference to how we do things. And now most of my department, the part that I manage the most closely, is funded by other divisions by the scientists to work on their problems. So those problems I pointed out to you are all ones where we're funded by the science division to work on their problem, not computer science. So unless there's any questions that need to be answered now, I think I'm going to turn it over to Sarah, and I'm going to stop sharing.
Thank you, Deb. That was amazing. Are there any questions for the moment? I don't see any prompted yet. If no one else has a question, I have one. What actually prompted you to go back and look at those projects to find out that there are only 10% in use still? Well, what was the trigger for that?
So I mentioned that we were, that our program manager was retiring. I had just gone through the Haas Business School executive management program, which was like a 2-week thing. And one of the big things that one of the instructors had touted was strategy and doing strategy. And I thought, what do we have to lose? We're about to disappear. You know, we're a group of 25 people. I said, well, what do we have to lose? Let's try strategy. You know, we're in the best position to do strategy because we can't hold on to what we were doing. It's gone. And so we started a very intense set of strategy sessions, and we started working on the strategy. And Dan Gunter, who still works in the department at one point, and Chuck McParland, who's since retired, both independently said, you know, while we're thinking about what do we wish we were doing, let's look at what we've been doing has been working, because they were both advocating that we work much more closely with the scientists. And they said, as part of that, let's go look at how well we're doing that now. And I said, yeah, let's go talk to all those people who are sure we did great work. And that's what prompted it.
Oh, there is a question. Can you see that too, or?
Yes, I can.
In the chat.
So in the original approach, and that's why in my slide, if you noticed, it was subtle and I didn't point it out, but in the first slide where I showed the computer scientist's approach, the screen with the computer scientist was full of stuff. And in the second one with the HCI approach, the screen was blank. When we approached them as computer scientists, we approached them with a set of, these are the things we know how to do. And these are the things we're funded to do. And said, can we help you with those things? And so we started out by saying, we have an agenda and we have something we love to do. And for every scientist, they have something they love to do. I mean, that's why you become a scientist, because you love doing that thing. And so when we came in and said, this is the thing we love to do, can you help us do it for you? They said, sure, we'll find a way to help you do it for you. But when Sarah came along, she said, she walked into them and she said, what are your challenges? what is it that blocks you? What things do you need? She didn't come in with an agenda of, I have these 5 tools. Which of these 5 tools would you like? She came in with, how do you work? How do you go about doing the things that you do? And what are the challenges in it? Which were never questions we really asked. If we did ask them, we asked them in the context of our tool. And it was viscerally different. It's weird, but that little shift of the knob was a massive difference in the answers to the question. And not trying to assume you understood it in one session. I always assumed I understood the problem within like 30, 40 minutes. And as computer scientists, we're kind of trained that way. And Sarah took meeting after meeting after meeting, and it was driving me crazy until I realized that all the first 5 things we would have built were wrong.
So just, I don't know if everyone can see, the question was what the actual difference was between Sarah's approach and Deb's approach. I have a last follow-up question on that. I also come from a CS background, and I see, you know, the typical grad student project, the thesis, the big thing that you work on for 5 years, 6 years, depending on the country and project. And it usually immediately after graduation, it just dies. It's gone. Is that a little bit where that comes from, do you think? That
No,
we have this,
I
there's
spent
no
a lot of
sustainability idea in, yeah.
I spent a lot of time thinking about this because it was kind of disturbing to realize that everything I was doing, I was just really wrong. You know, I was like, and I thought, okay, it's me. But then I've watched every computer scientist we've hired has exactly the same problem. And I think it's all of our training. You know, you're trained in computer science and in engineering often to really say, you know, I've got a hell of a toolbox. It pretty much spans the whole space. You tell me the problem and I'll find the tool to solve it. And I've got such a good toolbox that I know I have the tool in it. You just have to describe, you know, as a mechanical engineer, I mean, you just have to describe that you need something that changes the, you know, the speed of this thing turning to this thing turning speed. And I go, oh, you need gears. Right? I immediately know the answer to the problem. It's gears. I just have to find out what ratio you need and how many gears. Right? It's kind of like that. I mean, we're really trained for this. We have a toolbox. Any problem can be solved with this toolbox. You just need a little bit of description. And we're also trained to believe that the way to solve a problem is to understand just enough about the problem to build the framework and to build most of the underlying infrastructure, and then build the surface part to meet the user's needs. And I really believed that until I watched Sarah build the surface and explain to me that 90% of what I would have built in the infrastructure wasn't ever needed.
Yeah, I see the point. With the new understanding that it's crucial to contextualize issues first, are your teams becoming more interdisciplinary? That is a good question.
They absolutely are, and almost all of our teams are half domain scientists and half computer scientists. And it helps keep the computer, it helps teach the computer scientists to get rid of a lot of their, what I'm going to call ego. It's not quite the right term for it, but that feeling that I always know the answer. And it helps tremendously because, yeah, they have an assumption that the domain scientists don't understand computing at all. And once they start working with them, they start to realize, no, you actually do. You just understand it from a different perspective than I do. So I want to hand it over to Sarah so she gets to talk, because otherwise we're going to run the hour out with answering questions.
Well, I personally can go over. I don't know how it's for you.
Yeah, same here. So thanks for that. And don't know. I'm feeling very nervous now because I'm not sure I can live up to the image that has been painted of me, but you know, we'll give it a try.
And by the way, Sarah's always accused me of that. But she's always lived up to it anyway.
I don't know. So, okay, let's see. Hold on. Okay. So I'm going to be talking about a little bit more about the design process and specifically about designing for expert use. And so this is a different kind of terminology than what Deb used. And I think it's a little bit captures more than just the scientists that we work with. I think that you could see, like, you know, all the science use cases that, that we're dealing with. But I think in data science and working with domain scientists, they might not necessarily be these kinds of like basic science researchers or something like that. So we already talked about my background. So let me talk a little bit about what I mean by expert use software. And so I'm specifically talking about work tools and business software for domain experts. And so you did see what that looks like at Berkeley Lab. It's generally focused on the sorts of daily work where new users quickly become experts. And that's partially a product of the sort of repetitive use of using the software every day for your daily work. But it also might be, you know, when a new person comes on boards, they get some specific one-on-one training for that. And particularly what I'm referring to, it can often be very specifically geared towards specific collaborations or specific internal teams in a company. So a lot of times these software tools are very domain specific. And so this kind of contrasts with how you design for other sorts of like commercial use software or software that's for entertainment or recreation. It's just a little bit, I think that those software, it has generally a broader audience than the kinds of software that we're talking about, and maybe sorts of like different goals and different sorts of tasks that are involved there. But in either case, whether we're talking about expert use software or we're talking about more commercial and other types of software, the UX design process is kind of similar. It's kind of basically the same thing. And I think these might be things that you guys talk about at MIDS. I'm not really sure. I know in MIMS, we talked about these things a lot. But basically, the process looks like you go through a research phase where you're doing your needs assessment. You're trying to understand, in our case, the user's work, the context of which this will be used, and kind of evaluating what the currently available tools are and what those limitations of those tools might be. We go through a design process at various different levels of fidelity. Like Deb said, I have been known to bring paper to a meeting. So I start out at lower fidelity and move on up. And part of that iterative cycle of moving through the fidelity and the design, we do evaluation, typically usability studies, sometimes follow-up interviews and those kinds of things. For expert use, there are particular challenges in each of these different phases of the design methodology. And so you could probably hear it in Deb's talk. Expert users have a lot of really deep domain knowledge, right? And they often have very complex work processes. They work in very technical environments. And so, you know, if I'm speaking to an astrophysicist and they'll start talking to me about redshifts and flux calibration, or they'll start saying how it's so challenging to transfer their codes from CPUs to GPUs, all these things sound like foreign language to me. I don't, you know, it's like a lot of these technical details kind of go over my head. That's where having a recorder at the interviews can be really useful when that happens. But that's some of the challenges when you're trying to interview and learn about these kinds of work environments. In terms of design, typically when I come and do a design at Berkeley Lab, I'm usually doing something that is graphical interface in nature, but sometimes the problem is actually requiring something more like an API or command line tool. And some of these tools that they need have to work with supercomputers, and they work with algorithms, and they work with large amounts of data. So it's a different kind of design than what you might see in other kind of commercial software. And then in terms of evaluation, sometimes standard usability testing works really well and sometimes it does not. And so, for example, if you're building a tool and it kind of replaces an old tool or it replaces a manual process, standard usability testing works really well, actually, I think. But if you're trying to introduce a new process, sometimes usability testing might only really capture the novice experience. Or for example, if what you are designing is an API, evaluating APIs is still really an emerging area. And I think that there's still a lot of work to be done to develop the standard practices in that area. And so there's a lot of different challenges. I personally really like working in this particular space. And I've been thinking a lot in terms of what are the sort of design guidelines when working in this area. And so I'm going to share, these are really a work in progress, but these are some design guidelines that I think are particularly relevant to data science tools. And so in the research area, and I think it's really important to understand the work processes and goals, but also the users' motivations and their values. And when it comes to the design of a data science tool, I think it's really useful to think about designing for user control, for transparency, and for user efficiency. And finally, in terms of evaluation, I just really encourage finding any opportunity to gather feedback from stakeholders throughout the design process. And, Deb kind of shared like the story of don't just like go in your hole and build this tool and then, present it at the end. I really encourage the sort of continuous feedback and engagement with the stakeholders. And this even applies for something like an API, which is not something that we typically see a lot yet, but I think that is still an emerging area. But through all of this, I think the main point is that devoting time and resources to user research and user engagement is really key for the success of these types of tools. And so I'm going to spend the rest of the talk just kind of going through examples that will hopefully illustrate some of what these design guidelines really mean. And feel free to interrupt. I'm going to go over this pretty superficially, but feel free to interrupt if you want more details, or you can email me afterwards if you want to get a little bit more understanding of what these examples are about. And so in terms of the first guideline, which is understanding the work processes and goals, I think this is really important in terms of helping you understand what it is that you actually need to build. And in particular, if what you're building is something that's going to replace an old software or replace some sort of manual process, I think this is really useful. And so in this example here that I'm sharing, this was work that I did, actually my very first work that I did at Berkeley Lab, which was for this collaboration called the Supernova Factory, which is an astrophysics collaboration. And their main science goal was to try to find as many supernovae in nearby galaxies of a particular type as possible, and finding them really early in their phase of explosion so that they could take pictures every night of the explosion and kind of get like the full phase of what that explosion looks like. When we came, it was like me and Cecilia, when we came in and started talking with this group, they were using this interface to the left here. And you can't really see the details, but the main point of this interface was that it was a search interface. And so you could, put in all your search criteria in order to be able to pull up a particular supernova and learn about what observations were taken of it and enter in some data about it. But what we noticed when we were watching the scientists using this particular tool was that in addition to this tool, everybody would have their own notepads or like files that would have a list of all the supernovae that they were currently tracking. And this was a list that everybody had the same list, right? So they would go down their list and then search it into their search interface. And it just became very obvious to us right away that that a search interface wasn't really serving their needs and their goals. What they really needed was a tracking system. And so something that would show their current list of supernovae that they're tracking and what stage it was in, and whether there needs to be telescope time scheduled for it or not. And so I think that, you know, these kind of early interviews and observations can really reveal some of those underlying workflows. And in particular, if you pay attention, if there are shadow systems like notebooks or files, that can be really revealing in terms of what that underlying workflow looks like. Another guideline is to understand user motivations and values. And I think this in particular is useful, especially when you're trying to introduce something that's new to, like a new process into somebody's already pre-existing workflow. And this example I'm sharing here is a project called Deduce, which actually Deb is a PI on. And Deduce is really about helping users understand data change across data sets. And so, for example, if somebody built a model on a version of a data set and then a new version becomes available, understanding what changed between those two different versions can give a lot of information about whether the modeler wants to rerun that model on the new version or not. But one thing about data change is that the meaning of data change is, and what counts as meaningful data change is very dependent on your domain and your file type. And so it's hard to kind of make some kind of tool that can be really generalized and still meaningful across multiple domains. And so an early idea was to make a plugin framework for scientists to write their own plugins so that they could specify what their meaning of change is. And then they could use it in that framework that could then really efficiently run those data change analyses at scale using supercomputing resources. And when we were talking to users, one thing that came up, and I'll get this quote, this one scientist said, "If I'm going to go to all the trouble of coding my own plugin, why would I bother using your framework?" And I think this is like a common thing. I kind of really shows there's that especially for many scientists, there's this sort of tension between the time and effort that's needed to write code and the value you get by being able to efficiently use supercomputing resources and be able to run things at scale. And so those are the kinds of things that are really important to consider when you're making any software for people. And so not just because of this quote or just because of this particular motivation, but for a lot of different things that we saw in our interviews, we decided that what would be useful was to build a visual plugin builder. And so the visual plugin builder enables sort of the more exploratory work that's needed to understand data chains, but it also helps ease some of the coding burden of developing those plugins. And then once that plugin is built using the visualizer, then that output could run at scale. Next, I'm going to talk a little bit about some design guidelines. And so one guideline I think that comes up quite a bit is, especially with expert users, is designing for user control. And so expert users really often want to be able to, they really appreciate automations and they really appreciate algorithms, but they like to futz around, right? So they want the ability to be able to override automations, and they want to be able to tweak the outputs from algorithms. And so this is back again to another supernova factory example. And what this was a computer scientist had developed this scheduling algorithm in order to be able to develop a schedule of what particular supernova targets to observe at the sky at what time and in what order based on a set of priorities and the exposure times and that kind of thing. And I was tasked to build a UI basically on top of this algorithm so to enable it to run and then also to show the output of what that algorithm generated. And very quickly, as we were working through the design of this, I realized that this group really wanted to be able to have that algorithm run and give a schedule, but then for them, they wanted to be able to like switch this this target to the side, or like remove this other thing. So they wanted to be able to tweak the schedule, but the algorithm was not built with that in mind. And it had like very specific start and stop times, so that moving things around kind of messed up the schedule. And in the end, we did support this use case, but we had to duplicate a lot of the code in order to get that to work. And so I think that it's really important to consider these sorts of human in the loop scenarios before an algorithm is written, because there might be a need to kind of try, I mean, I think in this case, it would have been possible to decompose that, those various different steps into more modular ways, so that we could introduce some of that user control into the setup of this algorithm. Next, I want to talk about designing for transparency. And so algorithms and abstractions are useful, but they can't be black boxes. Expert users really want to know what to expect. And so this example came about from a set of interviews that we were doing about how scientists use supercomputing resources. And one of the things about supercomputing resources is that they tend to have a lot of different data storage and file systems, and in different places and stuff like that. And so managing your files across all these different data file systems can be really tricky and challenging, and it's something that a lot of people talk about. And this is actually a well-known problem, and I think that computer scientists have tried to address this problem. But one scientist gave a story about a particular data management tool that he used that did not solve this problem very well. And so he was saying that, you know, there was a data abstraction layer on top of all these different file systems. And so you would say, like, you know, open this file, and it wouldn't really matter whether this file system, whether this file is on like this node or that node. And so it was supposed to help like make things better and make things less complicated. But what he noticed is that, you know, sometimes he would open a file and he couldn't tell whether the file was going to be on disk on the node that he was logged in, or if it was going to be actually in the tape archive. And so the difference is, you know, one can open up within less than a second, and one might take 5 minutes to open up, but you had no way of knowing. So there was no way for them to build this sort of expectation of how things were going to work. And so it's just really important to design in such a way that users are able to develop the right mental models that really align with the underlying conceptual models. And I think, like, I don't have the example for this, and I wish that I was able to look it up, but this actually applies to machine learning algorithms as well. There was an example that I've seen where, you know, the more that the scientists were able to understand how the machine learning algorithm worked, the better they liked it, and the more they were able to trust it. So if there was one algorithm that was able to show all the predictive features and how that was weighted, then they could see that and they could verify that, and they trusted the output. But for some of these other types of algorithms where it's like really harder to say like what's going on and what's happening in there, they tended to trust the result less, even if the result was actually more accurate. They prefer to use a less accurate but more transparent and easier to understand algorithm. So that's just something to keep in mind. In design, I also wanted to talk about designing for efficiency. And so expert users really want to be able to do their jobs efficiently and without errors. And how that plays out is really dependent on the purpose of the interface and what it's supposed to do. But I think one really common type of design that I see a lot is like these sorts of data overview types of interfaces, like often these kind of tabular interfaces where people are trying to determine some sorts of trends or make some sort of decision based on that type of data. And a lot of times, and as is the case in this particular example that I took from Stitch Fix, it is usually an Excel spreadsheet that we want to build a UI for. So sort of replacing an old process. And typically when this happens, scientists and like domain experts will say like, they want to preserve all the data, right? They want to see as much data as possible, and they just don't want to sacrifice any of that. And data dense views are really good and really useful, but sometimes there's not always the most efficient way to make a decision. And so I like to follow these sets of guidelines for that type of use, where you really want to figure out what are the most important types of data in order to make a decision, and really show those prominently so that you can minimize what needs to be held in working memory to make that decision. But for everything else, the sort of more ancillary information or information that might be more relevant to a different type of decision, put it in another layer or in another view so that you can really improve the signal to noise for that kind of decision-making process. Finally, I want to talk a little bit about evaluation, and particularly early evaluation of APIs. And I think I mentioned before that developer experience is very much an emerging area. What I would say is that go ahead and try out the novel approaches for evaluating APIs before they are written, even if they seem weird or untested or kind of not matching reality. It's still really useful. And so we've tried out a couple of different sort of novel approaches to evaluating APIs. One is the one that I'm showing here. So I was actually working with a PhD student, and her background was in psychology. And so she came up with an idea to, we were given a list of API potential features, and we were trying to determine like what would be the highest impact of these features to implement. And so we gauged sort of our stakeholders' positive versus negative feelings towards those features, and also the strengths of their feelings towards those features, to kind of like develop this sort of heat map to just sort of determine like what are the best features to build right away and what can wait. Another technique that we've tried is sort of the paper prototypes of an API spec. So basically, having the API designer write out what the spec would be, it's not implemented yet, and then having potential users try to solve certain tasks by writing out pseudocode on a Google Doc. And so these methods are not perfect. Like they really don't match. They're really not like, don't really capture what it's going to be like to work with an API. But what it does do is that it provides a lot of really rich context for discussion and feedback with stakeholders. It also keeps them in the loop so that they know like, where are you going with this, so that they can provide their feedback at that point. And so I think that even if these methods aren't perfect, and I think that maybe the API usability community is going to keep on working and trying to develop some new techniques, I would say go ahead and try them out, because it at least provides a context for feedback, and you can use it as a more holistic approach in order to be able to understand what to do with that evaluation. Don't treat it like a hard science, right? Treat it more as guidelines for you to use as a designer and your own instincts in order to know which way to go. And so in summary, yeah, just to design software for expert use, understand their work practices and their motivations so that you build the right thing. And then keep in mind that expert users value control, transparency, and efficiency when working with data and data science products. And just try out usability testing of APIs or command line interfaces, even early in the process of designing and developing them, because the main point is to just try to gather feedback from stakeholders throughout the design process, rather than waiting at the end when it's completely done and then giving it to them. So with that, I'd like to thank all these people, and that's it. If anyone has questions, I'm happy to take them.
Thank you so much. Are there any questions? So no one is typing questions right now, then I'll take that from them. I'm curious about what you've shown about the use, what you wrote for the physicists, the supernova tool.
Oh, this one? Or yeah. This one is Deduce,
is that area independent? Could you use that for any, do you think you could use that for any science field, or is that pretty specific to physics scientists?
Yeah, so this example that I'm showing here is the physics example, but actually we're taking an approach of a file type right now. So there's going to be, this one is a FITS file, which is more commonly used in physics, but we're also looking into HDF5 and CSV and other types of file types. So I should bring like the other examples of what those look like, but part of it is having like some sort of like small inspection of an example file and be able to use that to do some exploratory looking at what the file looks like and drawing out your comparisons, and then be able to say like, these other files are very similar to this file, so go ahead and run your analysis at scale on all these other files. So it's kind of a model of, you know, inspect a small sample and then generalize it to at scale.
Okay, understood. Thank you. Yeah. Yeah, the amount of people here is reduced now.
Yeah, it's late.
It's becoming late. I don't see any more questions. I could keep talking with you for the next hour. I have a lot of very specific questions. I'm not sure how interesting they are for the others. Maybe we have another chance to talk. I'm really curious about a few things you're doing.
Oh yeah, and you feel free to email me and send me questions as well.
Oh, thank you. Yeah, thank you so much for coming, for making that happen today and giving all these insights. And yeah, people have been already asking, have told me, I can't come, is this recorded? So it will be recorded, there will be a recording. You can, I hope I can make it available to you. Please come to me if you want that. And with that, I hope to see you again in the future.
Okay, thanks everyone.
Thanks
Bye.
for inviting us. Thanks everybody.
Sure, good night.